Hello everyone, welcome to another session on the deep learning series. We'll continue with the discussion on activation functions. So as discussed previously, this is what an activation function is used. Right? This is where activation function is basically used. So after you're done with your normal cross product multiplication, where you multiply the weights with the inputs, and where you add the bias terms, then whatever output you get, you basically pass it through a function which is called as the activation function, and that's whatever output you get is basically the output of the nodes, right? So one of the main reasons for using activation functions are activation functions basically introduce non-linearity in your neural network models, right? Without say any of these functions, what you basically get is more or less a linear regression equation, right? Because you're only multiplying, right? You're doing more cross product and you're taking additions. Because of that, you mostly end up getting linear regression type of model, right? So what this is what activation does. Activation functions basically introduce non-linearity to your model, right? So one more sort of requirements for activation functions are activation functions should basically be differentiable, right? So one of the main reasons for this is because as we discussed previously, in any neural network you will have two stages, right? One is your forward pass, and the other one is your back propagation or backward pass, right? So what happens in back propagation is where you take the derivative with respect to your weights, right? So suppose in this particular example, you move from say output layer to your hidden layer H2, then hidden layer H2 to hidden layer H1, hidden layer H1 to input, right? So as you sort of move your gradients, so as sort of back propagate, right, over there you need to calculate your derivatives. While calculating derivatives, you need to calculate derivative activation functions as well, right? That is one of the main reasons why you would need the activation functions to be differentiable. Okay, so as discussed again previously, there are two types of activation functions. One is your linear activation function, other one is your non-linear activation function. So the first one is basically a linear activation function. So this is sort of pretty straightforward, right? So you basically have it's a straight line. It's a linear function, right? So it's the equation. The equation for the particular for this particular linear activation function is nothing but f of x is equal to x. So whatever input you give to the function, you just basically get that as output. So one one major drawback of that is it does not sort of add any sort of non-linearity to your to the neural net, mainly because it's more or less an extension of your linear model, right? So I think that's why this is not majorly used anywhere. Coming to non-linear activation functions, these are the ones which are actually used a lot. The first one which we are going to look at is basically what is called as your sigmoid activation function, sigmoid or logistic. So I think this you would have commonly seen in logistic regression, right? So the formula basically is sigmoid, 1 by 1 plus e power minus x, right? So when do we use this? Before that I think you can just have a look at the plot of the activation, plot of basically the sigmoid curve, right? So basically whatever values of these are values of the function. So you see that the values the value of the y will always be between say 0 and 1, right? So from this I think you can definitely say that where it is commonly used is basically whenever you have any binary classification, because you know that your probability output will always be between 0 and 1, right? So range of this particular activation function is 0 to 1. I think this can be known from the graph itself. 0 to 1 is basically the range. Then function is differentiable. That we would have seen that we have seen in the calculation in the logistic regression gradient descent calculations, right? So we were able to find the derivative of the sigmoid function. And coming to the particular aspect of function. Function is monotonic. As you can see, monotonic is either always increasing or always decreasing. So when you actually move from your left to your right, you see that the value is always increasing. Right, the value of y is always increasing. So this is an example of monotonic function. But derivative of this particular sigmoid is not monotonic. Okay. So this is the second type of activation function, basically a sigmoid activation function. So the another important activation function is basically your tan h. Tan h is nothing but your hyperbolic tangent activation function. So as you can see over here, it also follows the profile of it is very similar to your sigmoid function as well, but one major difference is basically your range. Your range is basically between -1 to +1 is what is your range, right? So basically what would happen is negative inputs, you would basically get sort of negative value, and positive inputs you would basically end up with getting a positive value. The range of sigmoid was 0 to 1, 0 to +1. Range of your tan h is -1 to +1. So coming to what is the actual formula of it is nothing but 2 by 1 plus e to the power of -2x minus 1. This is what is tan h function formula. Coming to range is -1 to +1, which you can see from the plot. So function is differentiable. That is one. The other one is you can clearly see from the graph that function is monotonic, but derivative is not. And it's commonly used whenever you have any binary classification use cases. Again, it's mainly this particular activation function is mainly used in classification use cases only. The next commonly used activation function is something which is called as Relu activation function. Relu is nothing but rectified linear unit. This is basically what is Relu. This is basically what is Relu. Relu is nothing but max of 0 to x. So whatever value you get, you just basically take a maximum of 0 to x. So this is you can think of this as mostly a linear function, right? But one major difference would be you are sort of restricting it to only positive outputs, right? So it is, so whenever the value of x is right, when value of x is less than 0, your output will be 0 only, right? So correspondingly its range would be its range would be from 0 to infinity to take any value. Again, from the graph you can see that function is monotonic, similar to your sigmoid as well as tan h, but one major difference is over here your derivative is also monotonic. So Relu is used commonly, at least in few hidden layers. So, but one sort of major drawback with that is, since negative values become 0 immediately, right? Because it's the function is nothing but max of 0 to x, correct? So since it becomes 0 immediately, that's actually sort of a big drawback, because this is not sort of able to handle negative values, right? So it's not able to fit or train negative values. So this is one major drawback. So in order to overcome this drawback, the next activation function was basically proposed. So this is something which is called as leaky Relu. Leaky Relu is nothing but basically what it tries to basically fix is that negative value problem. As you can see, you can whenever there is a negative value, basically make it as f of y is equal to a of y. This is where this particular part is, the f of y part is where you're basically trying to take care of your negative values, right? From this, range is -infinity to +infinity. So value of a is usually sort of fixed. It's either 0.01 or in that order. So both so there's again one more type of Relu called as randomized Relu. Randomized Relu is whenever value of a is not 0.1, right? Whenever value of a is not 0.01, it's basically called as randomized Relu. So you can sort of randomly pick a value for a. Coming to the nature of the graph, nature of the function, it's both Relu as well as the randomized Relu are monotonic in nature. Derivative is also monotonic. That can be clearly seen. At least the function can be monotonic. Nature of the function can be seen from the plot. Derivative of this is also monotonic. So these were sort of the important activation functions which are commonly used. In order to, this is again just aggregation of all the commonly used activation functions. The first one is, I think, identity or linear function. Next is your binary function. This is binary function.